Hi, my name is Keerthana Jegatheesan, and I'm a PhD student at the Universidad Decomposition in Chile. I'd like to talk about a project I've been working on in the past year called BUDDI-MaNGA, which is a spectroscopic survey of galaxy bulges and disks. And I'm going to be focusing on exploring bulge formation scenarios in spiral galaxies in the framework of this project. To start with, we know that galaxies grow and evolve throughout their lifetimes and go through morphological transformations. Here on the right is an image of the Hubble sequence in the local universe showing different morphological types. And on the left is a schematic showing the many pathways and physical processes affecting these morphological transformations. For example, galaxies may grow by accreting smaller satellite galaxies or through star formation episodes, but they can also evolve when their star formation has been quenched by external or internal physical mechanisms. As it's shown here, quenching can occur as a result of major merger events or through AGN feedback, but the opposite can also occur when a passive bulge galaxy is rejuvenated by a minor merger. Additionally, environmental effects like ground pressure stripping and harassment can strip away the gaseous fuel needed for star formation in the galaxy, leading to its passive evolution. All these complex evolutionary pathways lead to different morphological endpoints in the Hubble sequence. These processes leave behind different signatures on the galaxy components like the bulge and the disk. Tracing back the star formation histories and the individual stellar populations of individual components would help us understand which processes triggered a galaxy's transformation and evolution. One common way of doing this is through photometric bulge disk decomposition, and this is done by taking the image of a galaxy and fitting the light profiles of the bulge and the disk, which gives you two-dimensional models of each component by creating wavelength-dependent models. From the fit, we can then extract the observed magnitudes and structural parameters like the size and Celsius index. And for multi-wavelength data, this can be done with all band images simultaneously. If you're interested in studies using photometric multiband bulge disk decomposition, I encourage you to have a look at Kalina Netkova's contributed talk. The large availability of photometric data has allowed us to study photometric stellar populations in a statistical way through the decomposition techniques. However, we often hit the H-metallicity degeneracy issue. To break this degeneracy, it is ideal to extend this concept to spectroscopic data to extract the bulge and disk spectra so we can better study the stellar populations independently. This is where BUDDI comes in. So BUDDI, or the bulge disk decomposition of IFU data, is a tool that was developed relatively recently as a wrapper for GalFit-M, which is itself a multi-waveband profile fitting tool. BUDDI extends the idea of multi-band fitting to the many wavelengths of an IFU data cube. So using GalFit-M, it models the bulge and the disk of the galaxy in each image slice of the data cube, which is by creating wavelength-dependent models. The concept of multiband fitting in general showcases a boost in signal to noise by making use of information from all available bands. And this is exactly what BUDDI does with the many wavelengths of an IFU data cube. At the end, BUDDI gives the clean bulge and clean disk spectra with minimal contamination of either component on the other, so representing pure bulge and pure disk spectra. While BUDDI has been tested and used on studies with small samples of individual galaxies, this is the first time it has been used for a statistical study on the MaNGA galaxies. BUDDI-MaNGA is a spectroscopic survey of galaxy bulges and disks in the local universe up to redshift of 0.15. Our sample uses the 16th data release of SDSS MaNGA, limiting ourselves to galaxies observed with the largest IFU sizes, which are the 91 and 127 fiber IFUs. This is because previous tests had shown that only these IFUs have a field of view large enough to perform bulge disk decomposition. And, the initial fit parameters were set to those from time of value-added catalog, and the galaxies were modeled with a central Celsius component representing the bulge, and an extended exponential component representing the disk. With BUDDI, we were able to extract the pure bulge and pure disk spectra of about 900 galaxies, covering a range of morphologies from early types to late type galaxies, and covering a range of stellar masses as well. So this is an image of a galaxy in the BUDDI-MaNGA sample. The one on the top shows the SDS's GRI image overlaid with the MaNGA data, with the MaNGA field of view, and the one on the bottom shows the MaNGA data cube image. As before, we fit the image slices of the data cube with a Circic bulge model and an exponential disk model, which are shown down here. The combined Circic exponential model is shown on top. And this is the final output from BUDDI. We have the pure bulge spectrum in red, the pure disk spectrum in blue, and the combined bulge plus disk spectrum in purple. This overlays the observed spectrum in black, which is just behind it, and we can see that the combined spectrum from BUDDI has managed to fit the observed spectrum very well. From these decomposed spectra, we can then extract the stellar populations that exist in the bulge and the disk separately by running them through a full spectrum fitting tool like PPXF. Following the bulge disk decomposition, we look at the resulting bulge to total ratios as a function of morphological T-type. And despite the high scatter, we can see a clear trend shown by the median black curve. The bulge to total ratio, which measures the bulge dominance of a galaxy, decreases from ellipticals on the right. It decreases from ellipticals on the left to spirals and irregulars on the right. In this work, we focus on spiral galaxy sample from the SA to the ST types, and we split the sample into two as the early type and late type spirals. The early spirals from SA to SBC show a higher bulge dominance, which are likely to host classical bulges. And the late type spirals from SC to SD, on the other hand, show lower bulge dominance and are expected to host disk-like bulges. Moving on to our results, we performed a full spectrum fitting on our clean bulge and spectra, and were able to obtain the mass-weighted stellar populations and reconstruct the star formation histories of the bulges and disks of these galaxies. The question I'd like to answer here is, when did the bulges and disks of the spiral galaxies assemble their stellar masses? And we start with the early spirals on the slide. On the right, we have a couple of SDS's images of these more early type morphologies. And here we have the star formation histories of the SA and SAB types in the upper panels, and the SB and SBC galaxies in the lower panels. This is represented by the mass fraction assembled by each component as a function of the look back time, with the ages in each panel starting from the age of the universe on the right, moving towards present times on the left. These plots are color-coded by the respective disk and bulge masses, with the highest masses in red and the lowest masses in blue. Now, when we consider the bulges in these two panels, we can see there's a clear trend in the stellar mass. These high mass bulges in red and orange seem to have assembled a majority of their stellar masses very early on in their lifetime within a very short and narrow time scale. This is likely indicating they formed through a single star formation episode and contain older stellar populations. As we move towards intermediate and low mass low mass bulges, going from green to blue, we see that the time they take to assemble their masses also becomes longer. These low mass bulges are likely to host relatively younger stellar populations. These trends are highlighted by the thick black curves in the plot, with the dot dashed line representing the average of bulges over 10 solar masses, and the dashed line below representing the average of the bulges less than 10 solar masses. Looking at the disks, we find that such a trend in stellar mass is almost non-existent, since the high and low mass average lines lie almost on top of each other. They show a higher fraction of extended star formation over longer time scales with multiple episodes of star formation. And now, following with the late type spirals, we again show the SDS's images of these morphology types, and it's clear even by eye that the bulge is not as dominant as those we saw in the early type spirals. we can see that the bulges no longer show no longer follow this trend in stellar mass, and it's interesting to see that these bulges are less massive as well. Their star formation histories are also reminiscent of those of disks, even showing extended star formation episodes towards the present time. These are expected to host younger stellar populations than the classical early spiral bulges. I'd like to further emphasize the stellar populations hosted by bulges in this slide. So here I show the difference in the stellar ages of the bulge and the disk on the y-axis against the difference in the metallicities of the bulge and the disk on the x-axis. The color coding is again in terms of the bulge stellar mass, and each panel shows relative stellar populations with T types increasing from the left towards the right. This is a quick schematic of the positions of relative ages and metallicities in the plot, with the bulges that are older than the disk occupying the upper regions and the bulges younger than the disk occupying the lower regions. The more metal-rich bulges sit on the right of this plot, while the more metal-poor bulges sit on the left. We can see that in the early type spirals, the majority of the bulges are massive and contain relatively older and more metal-rich stellar populations as compared to their corresponding disks. This is as expected by the traditional picture of bulge stellar populations. However, this fraction of older and more metal-rich populations decreases as we move towards the later spiral types. And at this point, in the SC and ST types, these show bulge stellar populations that are more or less equally spread as old and metal rich, old and metal poor, and young and metal rich compared to their disks. Clearly, the bulges of the late spirals show disk-like behavior in their star formation histories as well as stellar populations. To conclude, we put our results into perspective to try and understand how the bulges formed in early and late type spiral galaxies and what processes shaped them. We find that bulges in the early spirals form a majority of their masses in a short and narrow timescale, which suggests that an external process like a major merger has influenced the stellar populations. These stars would have formed very early on and later converted into the bulge as a result of a merger event, which exhausts the gas and prevents further star formation, which will lead to the older evolved and more metal-rich stellar populations that we see. These classical bulges show stellar populations that are nearly similar to those in S0 galaxies. On the other hand, bulges in late-type spirals form their masses through a longer time scale, which could imply that internal processes are at play here. The extended star formation histories we found are indicative of a bulge formed through a gentler, slow, secular evolution of the disk and show stellar population properties similar to the disks. I must note that the wide range of stellar populations we see, particularly in the late spiral bulges, is something that we're still looking into at the moment. To summarize, with BUDDI-MaNGA, we're building the first statistical sample of bulge and disk spectra, and these allow us to reconstruct individual star formation histories of bulges and disks and analyze the stellar populations they each host. In the project, we look for clues imprinted on these components to get a picture of their formation and evolution across different morphologies, stellar masses, and environments, and how different physical processes influence their transformation. The BUDDI-MaNGA project has started to take off with the study of S0s in spiral galaxies, and if you have any thoughts or ideas or would like to collaborate, I invite you to get in touch. Meanwhile, thank you, and I hope to see you in the discussions.